the square. Okay, so we have S as the sum of the squares of the divisors of 480. And we know we can rewrite 480 with its prime factorization of 2 to the 5th times 3 times 5. So there's a really clever trick to like writing S. And if you're familiar with trying to find the sum of divisors, it's like really similar to that, where you just do like 1 plus 2 squared plus 2 fourth plus 2 to the 6th plus 2 to the 8th plus 2 to the 5th. And then you multiply this by 1 plus 3 squared and then 1 plus 5 squared. And you can try to convince yourself that this works, because when you multiply out this this expression here, you're gonna achieve like every single square of the divisors of 480. So then we can just easily calculate S manually, and we can see that this value is just 4 to the 6th minus 1 over 3, like by the geometric series like identity, times 10 times 226, and this is just 260 times 65 times 21, and we can reprime factorize this as 2 squared.
Sorry to pause you. Like, Eric, did you let everyone to follow you? I feel like everyone's following me. So
Oh, wait, how do I do that?
I think it's on the top right corner. There's something like to follow you.
Yes.
Oh, there we go.
Yeah. So yeah, because we only can see part of your writing. Yeah. Okay.
Yes. So I have a question.
Yeah, go ahead. Yeah, if you want to ask
Yes.
the Eric question, just go ahead, please.
Yes, but how do we know that the sum of the squares of the divisors are 1 plus 2 squared plus 2 to the 4th and so on? So in other words, just tell me the rule that shows that the sum would be that.
Well, there's not really a rule per se, but it's more of, if you think about it, like if you multiply this out, you're gonna have what, 1, 2, 3, 4, 5, 6, 1, 2, 1, 2. So you're gonna have 24 terms when you multiply this out.
Yes.
And you can kind of think that this exactly corresponds to the like 480, 24 divisors of 480 squared. Like you would have like 1 plus 2 squared plus 3 squared plus 5 squared, and then so on. And if you just think about it, that's just like 2 squared and then 3 squared and then 5 squared.
Oh, so you simply square 480, like you square their prime factorization?
Yeah, exactly.
Yes. And then how come it becomes like an infinite geometric series?
Oh, this isn't infinite. It just goes up to 6 terms.
Oh.
Yeah. I mean, you don't really have to bother with this. You could just like sum this out like yourself.
Okay. Thank you.
Yeah, no problem.
Is it fine if you zoom out just so I see everything?
Yeah.
Thank you. Thank you. That makes sense.
Mm-hmm.
And you just find the sum of divisors of S.
Oh wait, you just have to find the number. So then you just have S as this expression, and to just find the number of like divisors, you just do 3 times 2 times 3 times 2 times 3 for an answer of 108. Does anyone have any questions?
Yes, so the answer is 108.
Yeah.
And we get it by finding the sum, which we know is 4 to the 6 minus 1 divided by 3. And we get that it is 2 to the, wait, but how do we go from 4 to the 6 minus 1 divided by 3 to 108?
Times 6 here. 10 times 26 there.
Oh.
Because that's just the 1 plus 3 squared and the 1 plus 5 squared.
Oh, okay. Yes.
Okay. Yeah. Does that make sense?
Let me see. Yes, so how is 260 times 65 equal to 2 squared times 3 times...
There's also the 21.
Oh, I did not see that. Yeah. Maybe it's hidden. But yes, that makes sense. Thank you really much.
Okay. Awesome, no problem.
Thank you.
Okay, so for problem 2, maybe I can do it like above here or like to the side. Or maybe, okay, I'll just like erase this part and I'll do it up here. So we have an ellipse in the first quadrant, and an ellipse is just like a weird oval. and it's tangent to the x and y axis. So we could kind of like imagine it to be something like this. And the coordinates of the foci are 8, 12, and 7, 12. So the foci of the ellipse are going to be around 2 points that are like symmetric around both axes of the ellipse, such that any point on the ellipse, the sum of these two like distances are always going to be the same. So if we have the coordinates of the foci are 8, 12, and 7, 12, we want to compute v. So we have, by the definition of ellipse, that the distance between these foci and any point on the ellipse are the same. So if we just like take this point as where we want this like distance to be the same. Let me see. And we could also consider this point. So for this point, we have that this is a and this distance is v. So we can find that the sum of these two distances is exactly a plus v. And if we plug that into this part, that we have for each of these like two lengths, the sum of, let's say this is a, and this also is a because it's symmetric around this line. So this is also equal to 2a. And for these points a, we had the line from here is 12. And we have the distance here. This is v, this is 8. So we have this is v minus 8 over 2. And we know a 2a is this. So we have a is equal to a plus v over 2. And we can also write this as like a Pythagorean theorem because we know this angle is 90 degrees. And we have 8 plus v over 2 squared equals 144 squared plus, oh, sorry, just 144. 144 plus v minus 8 over 2 squared. And if we expand out these both sides, if we expand out this expression, we have that v squared over 4 plus 8v plus, wait, did I do that right? Wait, sorry, no. It should be, I think, 4v. And 16 equals 144 plus v squared over 2 minus 4v. And this is also plus 16 as well. And we find that this like v squared over 2 is v squared over 4. And this v squared over 4 cancels. This 16 and this 16 cancels. So we're left with that 4v equals 144 minus 4v. 8v equals 144. So we have an final answer of v equals 144 over 8, or this is also 18. And that's the answer for our second problem.
Yes. So because partially during the problem I did not expand my screen, I could not completely follow up to why a plus v squared is 8 plus v divided by 2 squared is equal to 144 plus v minus a divided by 2 squared. So what I first did, so as you did first, is you put an ellipse for as an example, and then you found, let's say the edge, one of the tangents are 0 because that's the definition of a tangent, and we know that this is 0. So then what we do is we find that there is this certain distance h, 12. So and that's where v is. No, wait, that's not where v is. So what is a foci?
The foci of an ellipse is basically 2 points, such that the sum of the distances from any point on the ellipse to these 2 points is always going to be the same. So like if we add these 2 distances and like these 2 distances, or like any 2 distances on this ellipse, then the sum is always going to stay the same.
So is it like the radius of an oval?
It's kind of like the radius of a circle, but since an ellipse is kind of like a stretched circle, it's going to be 2 points, if that makes sense.
Yes. Okay. So please give me 1 more minute, just so I can follow up to your solution. Second V12. V12. V minus 8 divided by 2. Right. And then we get 12. And then some A. And what is A in this diagram? Oh, A is the distance from one of the tangents to one of the point where in which point 812 lays. And then
Yeah, it is just the distance from these two foci to the point where it's tangent to the x-axis.
yes, and how do we know that one of the sides of this right triangle is V minus 8 divided by 2? So
Okay, so we know that that's like v minus a over 2. Because if we think of this as a line, and these are
yes,
foci like a and b, and we
yes,
have the distance, we have this is like 8, 12. So we know this
Yes.
length is a, 8, and this
yes,
is like v12. So we know this distance is v. So this is going to be v minus 8. And if we this like part is going to just be exactly where half of this is, because so that's just going to be v minus a over 2. Because if you think about an ellipse, the place where it's going to be like lowest is just going to be in the middle of the two foci, and since it's tangent to like this line, it's always going to be tangent where it's lowest, and that's just going to be between these two foci. So this is just where it's going to be like approximately tangent.
yes, yes, yes. Thank you very much. Yes, thank you. So and then you simply find out. Okay, thank you really much. Thank you.
Okay, awesome. Does anyone else have any questions? Okay, then that just should be these two problems done.
So Samuel, go ahead. Now it's your turn.
Yeah, okay, sure. Yeah, okay.
Uh,
Wait, so let me add the problem.
Yeah.
Is there any way you can insert an image?
Let me do it. Okay. Okay. Samuel, can you see the problem?
Yeah, I can. Thank you.
Okay. Yeah, you're welcome. Let everybody follow you, okay?
Okay, sure. Okay, so yeah, so these are my problems. And so the first problem is a combinatorics. It's a kind of interesting problem. It's a game style problem in which you are asked to analyze a game. So yeah, I've noticed that this problem did give some difficulty to attendance. So I will start with problem 1. So for problem 1, Alice and Bob play a game and they take turns subtracting 1 and 2. And the first player to reach 0 as one of the numbers wins. And we ask for like, given A and B, does Alice have a winning strategy to win the game? I'm asked to find the probability that, oh wait, I forgot. Given the find the probability that A and B are such that Alice has a winning strategy. What's this stick? Okay, that's stick. All right, so the idea behind this problem is a idea known as winning strategies. Oh, I mean, not winning strategy, winning positions, in which you consider a position and you basically think, okay, is this a winning position in which Alice has a winning strategy, or is it a losing position in which Bob has a winning strategy? In this case, given how the game works, it becomes natural to think, okay, each winning position depends on whether preceding winning positions are winning or losing. So we start off by considering some position XY. So we don't even care about A and B. We just first start looking at the game and playing around to see what we can find. Okay, so we start with XY. So from XY, suppose it's Alice's turn. If it's Alice's turn, she could remove. So in case you don't know, this right here stands for the number of the number in the first number, and Y stands for the second number. So Alice can remove 1 from the first number, 2 from the first number, 1 from the second number, and 1 and 2 from the second number. So Alice could do one of these moves to achieve one of these four pairs of numbers after she makes a move from this position. Okay, but notice that if one of these positions are losing, if just one of these positions are losing, in which if Alice starts in this position where the player that starts in this position loses, then Alice just moves to this position and Bob loses. Therefore, X and Y is a winning position. But however, if every single one of these positions, these pairs of numbers, will result in Bob, the player who starts first in this position, if for every single one of these positions they lose, I mean they win, then this would be a losing position for Alice, for the starting player, because regardless of what the starting player does, it will always turn to a position in which the second player has a winning strategy. That is the idea behind this problem. Before I continue with the calculations, does anyone have any questions? Yeah, the answer, Claire, the answer should be a 5-digit. Yeah, it should be 5 digits. A 5-digit denominator, at least. So does anyone have any questions regarding how I define winning positions and how we can deduce whether a position is winning based on previous? Advic, the answer is 6934 over 10201. It's looks bad, but the calculations aren't too bad. Okay, so now I'll go into the details. So remember, if all of these positions are winning for the first player, then this position is losing, and if just one of these is losing, then will be a winning. This right here will be a winning position. Okay. So now we can start from the simple case. Let's consider 1 and 1. Or even simpler, we consider like 1 and 0. If one of the numbers is 0, right? Or, yeah, let's just not do that. Let's do 1, 1 first. Because they have to be positive. Kyle, the numerator is 6934, not 7200. But yeah, it's close though, it's close. So good attempt. Yeah, this problem isn't easy if you don't know this winning strategy thing. Okay, so for 1, 1, so if Alice goes first, Alice can first just immediately remove 1 from this position and win. So this is a winning position for Alice. Well, about 1, 2. Well, same thing, right? Alice just picks one of these numbers and remove one, and Alice wins regardless. And if you just do this, you realize that any number of the form, any position of the form 1 and I is a winning position for Alice by simply, she just takes 1 from the first number. Likewise, for I and 1, this is also a winning position for Alice. 6800. Yeah, I will explain the problem first, and then I can, because 6800 is reasonable. It's pretty close, and yeah, it is 6934. That is the numerator. The answer is right here. This is the answer to the problem. Okay, so similarly, 2 and I must be a winning position for Alice, and so must I and 2. This is for all I. All of these are for any natural number I. All of these positions of these 4 types are definitely winning. Does anyone have any questions? Okay, if not, then we start with the simplest after 1, 2, I, thing. All right, so for this position, let's consider what's going on here. So Alice can make a move into one of 2, 3, 1, 3, what else? 3, 2, and 3, 1. Right, Alice, for one of her moves, she could get one of these 4 things. But you realize that once she makes a move, then it's Bob's turn. But Bob for sure has a winning strategy. He just, turns this into 0 and he wins. But Alice, regardless of what she does, must end with a losing position. So there must end with the winning position for the second player, which is Bob. So therefore, this one is a losing position, which means Bob has a winning strategy for 3, 3. Okay, what could be said about 3, 4? Well, for 3, 4, it's for sure a winning position. Why? Because Alice on the first move could just remove 1 from 4, go to 3, 3, give it to Bob, but we know this is already a losing position for the first player. So in this case, Alice would win, and likewise for 3, 5, Alice would also win. But what about for 3, 6? Yeah, again, we're faced with the same situation as with 3, 3. All of these positions you see are all winning for the first player, which makes this losing for the first player. Do you sort of see the pattern? This is winning position for Alice. With similar logic, she could just remove 1. This is a winning position. And with similar logic, this is a losing position. So for this, just based on this, suppose you don't have time, and maybe you just want to test 6, 3, maybe you want to test 4, 3, but it is just, you can instantly just guess that the answer for all the possible losing positions are the positions A, B, for which 3 divides A and B. If you really want to prove this, then, which I'd say is not recommended in the Amy, if you have this intuition, then just go for it, because usually these problems are not insolvable. But if you really want to prove it, you could just use some sort of simple induction. So you just consider, okay, for each of these A, B for 3 and 8 indeed divisible by 3, then you realize that for every move, it has to go to a position in which both numbers are not divisible by 3. So with induction, you could claim and stay and build yourself up. That's this problem. And if you want the details, it's basically 1 minus 33 times 99 over 101 squared. We use complementary counting to count all the losing positions for Alice. And the 101 is completely arbitrary. I have no reason for making it. I just chose randomly. And yeah, that's how you what's it? Solve the problem. So,
So I have
yeah,
so I have a question. I understand everything until you get 1 minus 33 times 99 divided by 101 squared.
oh, that step. I did not explain it fully, but
So 33, you get 33 because there are 33 ways that the first number would be divisible by 3.
exactly.
In addition, but then how are there 99 ways for the second one?
Uh,
Because shouldn't they divide both? Oh, wait. Wait, 1 second. Let me see.
oh wait, no, I actually made a mistake. I actually did it wrong. It should be A minus B. You know what? Yeah, wait. I thought this problem was a little too simple. Give me a sec. Oh, thanks for pointing that out. Thanks for. Oh my god. Oh, my brain is not doing what's supposed to be doing right now. So we know this. So making a chart could also be helpful because that's
Yes.
what I was doing when I was making the problem. But yeah, apparently I wasn't thinking that way when I was explaining to you a few seconds ago. But you know, this is a losing position. These two are winning. This is losing, right? This is 6. As it turns out, this position is winning, but this position here would be losing because, you know, look, right? This position is winning because of symmetry. And you can just simply repeat this process. And it turns out not for both numbers to be divisible by 3, but it's just 3 divides for all 3 divides A minus B. But the induction approach still works if you want to prove it.
Yes. Okay. So
Yeah, so then, yeah, just 1 and 3.
so 33 times 99 divided by 101 squared represents all the losing positions. Now, 33 we can get for the first one, and then 99 we get from the second one. I get how we divided by 101 squared, but
no.
the only thing, yes?
The 33 times 99 just was a third of 99 squared because you notice that for I made 101 so that this, if you exclude these original stuff, because none of them are for sure losing, it's a 99 by 99 square. And if you draw it out, you find out that it's clear that exactly 1/3 of them are losing positions.
Oh, okay.
Yeah, so it's just a third of 99 squared.
Yes, thank you really much for this problem.
Yeah, sure. You're welcome. I just wanted to include it because this has been a big topic recently. Okay, so does anyone have any questions on problem 1? Oh, and there's something, if there's no questions, I will go on to number 2. There's something very funny I find about number 2. It was just that number 2 is for sure harder than number 1. Yet 4 people solved number 2 by simply guessing the answer to be 0, which is correct. Yet nobody solved number 1, which I find very. They just guess. 4 people just guessed 0, and they miraculously got the second problem correct. Which I think is something bad on my part because I originally intended this to be proof that there exists no primes. But for the sake of this contest, I have to change it to find the number, which in this case is 0. Yeah, that's sort of a bad problem making on my part, but I think it's, I guess, somewhat nice in my opinion. The solution isn't long. So yeah, this problem is, I'd say, hard. If you've never seen this problem before, these types, then yeah, then this just becomes very hard. This is a Diophantine equation in disguise. So what you can do is you can write this as, you know, p times x squared, where x is an integer. Okay. Let's just say it's a positive integer for the sake of it. Okay, so what you do now is to look at this prime. This prime p just suggests taking this, considering this. So it p divides 48m plus 47m plus 1. Now we compute the GCD of 48m and 47m plus 1. This is, if you use Euclidean algorithm, turns out to be what? M minus 1 and 48. I'm not going to explain to you here for the sake of time. So yeah, that's that. And this right here for sure divides 48. However, because m minus 1 is not divisible by 2 nor 3. Oh, wait, no, that's the wrong way. Oops. 2 and 3 are both not divisible by m minus 1. Why? Because m is written in the form of 12k plus 2. So m minus 1 can't possibly be divisible by 2 nor 3. Okay, that's that. So given this, you realize that the GCD of this cannot possibly be divisible by 2 or 3, but yet it's divisible by 48. And yeah, it divides 48. I mean. How can this be? Well, only if the GCD is 1. And now we are in familiar territory, because what does this mean for this equation here? Well, this means that P must divide either 48m or 47m plus 1. Is this clear? Is this intuitive? If so, the rest becomes a case analysis. So I'll start with case 1. Let's see here, if 48m is equal to, if 47m plus 1 is the value divisible by P, then 48m must be a squared. And 47m plus 1 must be, let's see here, P times B squared. But then you're like, well, why must there be B squared and A squared? But remember, the GCD, oops, I switched to eraser. GCD is 1. This GCD, not this one. Oops, I don't know what I was thinking. It's this one, but this implies GCD. I keep switching to eraser. Give me a sec. All right. GCD of 48m and 47m plus 1. This is 1. Okay, so this is clear. And the other case is if we swapped it with like P here and no P here. So in this case here, let's see what's happening. Let's start off with, let me see. Considering what is the V2, the two-adic valuation of 48m. So what is V2 of 48m? And for those of you who are not familiar with V2, it's basically just saying how much prime divisors of 2 divide 48m. This is equal to the number of prime divisors of 48 plus the number of prime divisors of m. Okay, we know this. This right here is what? This right here is 4. What about this? Well, we do know that. Remember, m is of form 12k plus 2, which means m has a remainder of 2 mod 4, which means what? This is 1. Now you stand back and realize, how can this be? Is this a perfect square? The V2-adic value of this must be an even number. So this, therefore, is not a valid case. What about the other one? The other way around. Let's just, yeah, there.
I have a question. How do you know that V2 of 48 is 4? And what is V2 anyway?
I was explaining this, but V2 just simply stands for the number of divisors of 2 that divides n. For example, V2 of 16 would be 4. V2 of 6 would be 1, because 6 is 2 times 2. Yeah, this is two-adic notation.
Yes.
Okay, so where was I? Oh yeah, the second case. So, and now you look at this. In the previous case, we considered V2, but in this case here, this equation, this looks very difference of squareable, right? Because if you subtract 1 from both sides, you get this thingy. And once again, you could utilize this, or actually, that's one way you could do it, but actually, it's actually a Yeah, I don't want to explain this way. Yeah, this way is not good. It still turns out to be the right answer, but it's slower. And if you just really think about it, if you just take mod 12, it might seem random, but mod 12 is somewhat natural to consider given how close this is to 48. If you take this, you get negative n plus 1 has a remainder of b squared mod 12. And if you realize this, we already know what m mod 12 is. So this implies that negative 1, what is it? M has so negative 1 has a remainder of b squared mod 12. But now, how can this be? If you write it out, you see that actually b squared can only have a remainder of 0, 1, 4, or 9 mod 12. If you do 4 squared, it just becomes 4. 5 squared just becomes 1. You'll find out that every single value, every single possible b squared has a remainder of one of these, which promptly contradicts the top. So therefore, there's no prime numbers p. Or if you want, you can use quadratic residues, but yeah, that's overkill. Okay, so yeah, that's problem 1 and 2. I think I did spend a lot more time than necessary, but yeah, does anyone have any questions regarding any of the 2 questions? I find these skills kind of essential if you for the Amy last 5, or if you want to even perhaps go beyond Amy. So yeah.
I have a question.
Mm-hmm.
Now, while it isn't related to these specific problems,
Yeah.
when would Amy be like when do people generally take Amy? Of course, anyone can take it at any grade, but I'm just wondering. I'm a 6th grader, so I'm wondering whether I should know this material.
Oh, 6th grade. Yeah, 6th grade. I mean, it really depends on not how old you are, but rather how much of the material you understand.
Yes.
So if you really understand the material, I mean, you can literally take Amy like when you're 2nd grade, to be honest. If you understand somehow understand all the material in 2nd grade, then yeah, sure, you could go ahead and take. So it's not really how old you are, it's really how much you learn.
Yes.
Right. These problems, for if you want like something similar to 12, there's like one Amy 15, which was really related to this one. It's about difference of cubes. But yeah. If you don't understand these 2 problems, it's fine. Those are like higher end because I made these problems based on higher end Amy problems and even beyond that. So yeah, does anyone have any questions? Okay, if not, then I will give it to Catherine.
All right, hello. Okay. I'll move. Oh, why is my internet connection? Okay, whatever. So I'll move to here, I guess. Hello. Okay. Problem. I'll upload the. Okay. Let me see. Okay, so
Simple question.
yeah.
I don't understand why 1 plus 1 is 3. Are you writing this?
Oh, that's not me. I don't know who's.
Oh, okay.
Okay, all right. So here we can first start by drawing a graph. All right, so here we can start by letting DE be 1 and AE be X. So the reason we can do this is because we're looking for the ratios and the exact side lengths don't matter. And we notice that there are a lot of similar triangles because of the angles that they give us. So we know that triangle ABC is similar to triangle DCA, and it's also similar to triangle EAD. Does everyone see why that's the case?
So I have a question about that, why that's the case.
So we know the angles are, so we're given that angle DCA is equal to angle ABC, and they're both right triangles. Maybe I should draw this here.
Oh, now I get it. Thank you really much.
Right, yeah. So now we know that these are all similar. So we can, we can, why is it not letting me? So we
I have a
can,
question. Where's point F? Oh, it's E.
Oh,
right?
yeah, sorry. So yeah, that's point E. So now we can use Pythagorean theorem to label some more of the side lengths based on what we've written so far. So we know that from Pythagorean, AD is root x squared plus 1. And then by similar triangles, because the ratio of the legs, the short to long leg is 1 to x, we know that DC is x root x squared plus 1. And AC is just x squared plus 1. And because it's also similar to the big triangle, we have this as x times x squared plus 1. Sorry, x squared plus 1. So another thing we can utilize here is that we notice that angle BAD is also theta. Does everyone see why that's the case?
Wait, I have a question.
Yeah.
So, how do we know that DC is this? So is the square root of x squared plus 1? Because I don't really follow that.
Okay, so we can do that based on the similar triangles
Yes.
in here. So because the ratio of the so from Pythagorean theorem we from short leg to long leg is 1 to x, and from Pythagorean theorem we know that AD is root x squared plus 1.
Yes.
And then that means that AD to DC is also 1 to x, so that means that DC has to be x root x squared plus 1.
And then how do we know that AC is x squared plus 1? Is it also due to a similar triangle?
Yeah.
Thank you. And AB is x times x
squared plus 1. Yeah, my handwriting is not that neat over there. I can make it a bit better. So this is x squared plus 1.
Yes, so x times x squared plus 1. Thank you really much.
Okay, yeah, no worries. So now we know that this angle is also theta, and now we can use angle bisector theorem. So we know that from angle bisector theorem, we have AE over AB is equal to ED over DB. So that means that that means that ED to DB is 1 to x squared plus 1. So this is just x squared plus 1. And now since BEA is a right triangle, we can just use Pythagorean theorem again. So our equation is x squared plus x squared plus 2 squared is x squared plus 1 squared. All right, and then, oh, sorry, I made a mistake. This is x times x squared, so this is x squared. All right, so now we can just simplify this. So we can let another variable, for example, t, be x squared just to make solving a bit easier. So we have t plus t plus 2 squared equals t times t plus 1 squared. And then we can simplify this, and eventually we'll get t cubed plus t squared minus 4t minus 4 equals 0. And then we can factor this to t minus 2 times t plus 2 times t plus 1 equals 0. So we see that t equals 2 is the only solution. And then from here, we see that basically DE, so that means that BD is just 3. So we see that the ratio we want is just 3 to 1, which is 3. So
Wait, I have a question.
Yeah.
So my question is, how do we know? So I looked at it and I think there are 3 solutions to the equation.
3 solutions? Okay, where?
Wait, may you please go to
Here.
Wait, but how come t is not also equal to -1 and -2?
Okay, so first we have that t is like x squared, so it's not possible for yeah.
Because of the complex numbers. Okay. So t is 2, and then we know that t is the square root of 2. And then
yeah, so x is the square root of 2, but we really don't need x because BD is just t plus 1, so we can just say that it's 3 to 1.
oh, okay.
Yeah.
Thank you.
Okay, can we move on to the next problem?
Yes.
Let me upload the next problem. Okay, so from these values, it seems that cosine to the 4th 3 pi over 9 is the only one that's easily solvable. So we can just leave that out for now and just try to find the sum of the others. And to make it easier, we can try and convert it into an easier form. So hang on. So we notice that cosine to the 4th 2 pi over, oh, sorry. Cosine to the 4th 2 pi over 9 can be written as cosine to the 4th 7 pi over 9, and also cosine to the 4th 4 pi over 9 can be written as cosine to the 4th 13 pi. Over 9. And we can just leave cosine to the 4th pi over 9 as it is for now. So from these 3, we see that these have a pattern to them. You see that the difference of the angles is just 6 pi over 9, which can be simplified into 2 pi over 3, which is the period of cosine 3 theta. And we notice that let me scroll down. We notice that cosine pi over 9, cosine 7 pi over 9, and cosine 13 pi over 9. They all they satisfy this equation. They satisfy that cosine 3 theta is equal to 1/2. So these are the roots of this equation. Okay, so now we can expand this and write it as a polynomial. So we have 4 cosine to the 3rd this, and then minus 3 cosine theta is 1/2. And so we can simplify it further, I guess, into equals 0. And okay, so we can just let these be like, we can just let these be R, S, and T for now. R, S, and T. Okay, so we just need to find R to the 4th plus R to the 4th plus S to the 4th plus T to the 4th. Okay, so to do this, we can use this technique called, well, I don't really know the name for it, but you can just like lower the degree. So first we have to cosine to the 4th theta minus 6 is equal to 0. And we see that now we want to lower the degree because I don't, finding the, using Vieta and expanding it isn't easy. So we can write like this. And so now we can, okay, so now we can use Vietas. And if you use Vietas, you find that so R to the 4th plus S to the 4th plus T to the 4th is going to be 9/8. Okay, so 9/8, and we need to remember to add this to, because remember in the beginning we set this one aside, we set cosine to the 4th 3π/4 aside. Now we have to add it back in, and so the value of that is 1/2 to the 4th. So you put plus over 16, and from this you can get 19/16. Okay, does everyone understand this? All right, can I move on to the next one? Okay, moving on to the next one. Let me see what I can. Oh, shoot. Oh, the answer to this one was, the answer to 3.3 was 6, by the way, if anyone's wondering. Nice, okay. All right, so first we can try and simplify the cosine B, cosine C portion. Let me get the pen ready. Okay, so cosine B, cosine C is equal to, so by product to sum, cosine B plus C plus cosine B minus C.
I have a question.
Yeah.
I did not see where your writing is.
Oh, are you following me? On the
How do I follow you? I see your whiteboard, but like it looks enlarged to me.
If you go to the right part of the whiteboard, you can see all like the profile icon thingies. If you click the arrow and if you select.
Oh, now I see. Thank you.
All right, great. Okay, so for product to sum, we can get this. And then because you know that it's a triangle, so A plus B plus C is equal to 180. So that means that this is just because cosine b plus c will just be negative cosine a. So it's negative cosine negative. Oh, shoot. It's negative cosine a plus cosine b minus c over 2. So now we can substitute this back into our original equation. Okay, so we have 6 sine a minus 5 over 2 cosine a plus 5 over 2 cosine b minus c equals 9. So we just substituted that back into the original. So now we want to simplify this thing. And to do this, we can use this thing called auxiliary angle formula. So the auxiliary angle formula basically states that if we have a sine x plus b cosine x, so we can write this as r cosine alpha sine x plus r sine alpha cosine x. And then we can write this as r times sine of x plus alpha from the sum of angle formulas. And here we know that r is going to be equal to root a squared plus b squared. So the maximum value that that a sine x plus b cosine x will be able to have is just r, because the max of any of sine is 1, so it's just going to be r. And in this case, so we know that so in this case, the value of r will be the max will be root 36 plus 25 over 4, which simplifies to 13 over 2. So that will be the max of 6 sine a minus 5 over 2 cosine a. All right, so maybe I should, okay, over here. So 6 okay, so sine a minus 5 over 2 cosine a must be less than or equal to 13 over 2. So also so now we can look at this side. The maximum of 5 over 2 cosine of b minus c is also 5 over 2, because same thing, the max of any cosine is just is 1. But you see that they have to add to 9. They have to add to 9, and that requires that both of them be at its maximum. Both of these values to be at its max. So we know that it has to be equal to 5 over 2, and this has to be equal to 13 over 2. And from this, we know that cosine b minus c has to be equal to 1. So that means that b will have to be equal to c. And also from this, we see that sine a, okay, well, we see that sine a will be equal to 12 over 13, and cosine a will be equal to negative 5 over 13. So now we can like draw a triangle. From here, it's like pretty straightforward, because okay, this is a really bad drawing. Oh, why is my pen not working now? Okay, so we can. Okay, so A, B, C. And we know that angle B and angle C is the same. And we know that we're given that this is 6. So all we have to do now is, so first we can use law of cosine to find the length of AB and AC. And then after that, we can use the area formula using sines to find the area of the whole triangle. So we know that cosine A is equal to negative 5/13. So by law of cosines, we have 6, and we can let AC and AB be x. So we have 6 squared is equal to 2x squared minus 2x squared times negative 5/13. So 2x squared plus 10x squared over 13 is equal to 36. And then 26 x squared plus 10x squared is 36 times 13. So we know that x is going to be root 13. And then now we also know sine of A, so now we can use the area by sines. So area of ABC is equal to 1/2 times 13 times here we go, times 12/13, which is equal to 6. All right, and that's how we get our answer. Okay, does anyone have any questions?
Oh, thank you, Catherine. Yeah, I think, you have done a great job. All of you guys, like, Samuel and Eric and Catherine. Yeah, it's already 9 p.m. So anyone have questions? If you have questions later, you can email us. And for now, I think, it's already very late. And and let's call it a day. Yeah. Okay, then bye. For the next session will be on Monday. Okay. Yeah. Bye. We're gonna end the meeting. Yeah. Bye.
Bye, everyone.
Bye.
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 Have a wonderful time. Have a wonderful rest of your night.
Yeah. Yeah, we
Bye.
hope that you have learned a lot.
Bye.
Bye.
Bye, bye, guys.